So we've been talking about conic sections in the last few sets of videos, and it's important to understand that conic sections can actually be unified by one definition, and the basis of this definition is going to motivate us to actually use polar coordinates rather than Cartesian coordinates to analyze them. So in general, a conic section is the set of all points in a plane whose distances from a particular point, called the focus, in a particular line, the directrix, in the plane have a constant ratio. And it's what this ratio is will determine what type of conic you get. So in this generic picture here, all we're saying is that a conic is defined to be the set of all points such that the distances from point F to point P, so PF, divided by the distance from D to P, has some constant ratio. And that ratio we're going to call E because we're going to see that we define that to be the eccentricity. And depending on what that ratio is, you'll get a different type of conic, a parabola, a hyperbola, or an ellipse. So let's see if we can make sense of this idea in the next slide. So let's look more closely at this definition here. If P is a point on a conic section, and F is the conic's focus, and D is the point of the directrix closest to P, then E is defined to be PF over PD. And that can be written as a multiplication statement instead, which you're seeing there. And the constant E is called the eccentricity. And the value of E will determine what type of conic we're looking at. So if E is less than 1, then we're going to be looking at an ellipse. If E is equal to 1, we're looking at a parabola. And if E is bigger than 1, then we'll be looking at a hyperbola. It's not stated here, but it's important to understand that a hyperbola will actually have two directrixes. I'm not sure about the plural of that. It'll have two foci and two directrixes. So just keep that in mind. So using this definition, this all-encompassing definition of conics, makes writing them in polar form actually quite appropriate. And so the way it happens is, or the way it's done is that you place the focus, or one of the foci if you're dealing with an ellipse or a hyperbola. You place that at the pole. So this point F here is at the origin, or the pole. And we define our line to be out there, x equals k. So there's a little bit of a mix of systems here, right? X equals k is definitely a Cartesian equation, whereas this point here, r comma theta, is labeled in polar form. But it makes sense to do that, even though it's, there's an inconsistency of systems. It'll make sense in terms of what we're about to do. So remember that to define a conic, we're saying that PF divided by PD is some constant number, the eccentricity. So let's rewrite this as a multiplication statement. And then let's just come up with some expressions for PF and for PD. So PF is easy, that's just R. That's just the distance from the pole to that point. And PD we can find by just doing a little bit of work. So PD is this distance here in red, right? So how can we find that distance? Well, notice that the distance here in purple from the pole to that line is just k, right? Because that's the line x equals k. So that distance is definitely k. So all we need to do is find the length here in green and subtract that length from k. So this right triangle, which is very convenient, will help us to do that. So I know that to find, let's just say this is called x for now. Or actually, let's just use a, since x equals k is written over there. So we know that the cosine of theta is A over R, which means that R equals A cosine of theta. And now I have an expression, sorry, A equals R cosine theta. That's what I meant. So this is R cosine of theta. And so now I know that PD is just the length K minus R cosine of theta. So I'll put that right in here. Okay, and we usually solve conics to be in terms of R, so let's just solve for R here. So EK, I'm going to distribute the E and we'll get the R's together by adding this term to both sides. So now I've got R plus ER cosine of theta is equal to EK. And I'm going to factor out an R. And I'm going to switch the order of this just because it tends to be written with the K first, not that it matters. Dividing both sides by 1 plus E cosine of theta gives me that R is equal to KE divided by 1 plus E cosine of theta. All right? So that is one equation for a conic in polar form. And the type of conic is, as just to remind you, is going to depend on what E is. If E is less than 1, it's an ellipse. If E is equal to 1, it's a parabola. And if E is greater than 1, it'll be a hyperbola. So just notice that in this case we did all the analysis with a pole and then a vertical line with a positive k value, x equal to k. So there are three other orientations that we can think about. We could have done the same analysis where x was equal to negative k, so just imagine kind of flipping this picture sideways, and that'll just affect the direction of the conic, the way it opens. But we could also have done vertical lines at y equals k, and that would have, again, reflected a different orientation of our conic. So if you look at the next picture, you'll see what I mean. So we can switch orientation a little bit, and rather than doing the whole derivation again, I just want to point out that if we started again with this this ratio PF over PD being E, and then again multiplying through, then again PF is still R, and it's just the expression for PD in this case. So again, remember, this is the y-axis now, this is the x-axis. This distance here would be R sine theta, and so our distance here would be K minus R sine of theta. And then, therefore, that means that if you were to do the solving for R, you would have gotten this. So, whether or not there's a sine theta in this location here or a cosine theta tells you about orientation. If there's a sine theta, we'll see that, let's just say we're dealing with a parabola. The parabola is going to open up or down, and if it's a cosine theta, it'll open left or right. So the vertical orientation you can associate with sine, and the horizontal orientation you can associate with cosine. So this is all summarized in the next slide. So here's a summary of the polar equations for conics, and what you should really do here, if you to make this slide useful, is just to have your mind organize these in terms of, first of all, orientation based on whether there's a sine or a cosine in that denominator. So that's the first categorization you should do, and then secondly, where the conic is situated in terms of the direction. So 1 plus e cosine theta is going to result in a conic that's weighted to the left, whereas 1 minus e cosine theta would be one weighted to the right. Similarly, for a vertically oriented conic, 1 plus e sine of theta would be oriented downward. 1 minus e sine of theta would be oriented upward. I mean, these are all rederivable, but it's really it saves you time just to sort of internalize the idea first, and then it just makes applications a little easier. Putting it all together, we've got that the graph of a polar equation of these forms is a conic, and E is a positive number, that's the eccentricity, and we can categorize the type of conic based on the value of E. One thing to pay attention to is the overall form here. So whatever number is in the numerator, that is going to be E times K. And there's always a 1 that starts the denominator. Okay, 1 plus or minus E cosine theta. So the number in front of the cosine theta, or the sine theta, will always be the eccentricity, so long as there's a 1 before it. Again, the minus and the plus will determine orientation.